Segment 1. The Birth of Quantum Theory. Our story begins in the early 20th century, a time when classical physics reigned supreme. Scientists believed they had unraveled the workings of the universe. However, anomalies in experiments hinted at deeper mysteries. Max Planck introduced the idea that energy is quantized, proposing that it comes in discrete packets called quanta. This revolutionary concept laid the foundation for quantum theory. Albert Einstein furthered this by explaining the photoelectric effect, suggesting that light itself is made of particles, photons. These ideas challenged the classical wave theory of light and opened the door to a new understanding of the microscopic world. Segment 2. The dual nature of light and matter. In the quantum realm, particles exhibit dual characteristics. Light behaves both as a wave and a particle, a phenomenon known as wave-particle duality. Experiments like the double-slit experiment revealed that particles such as electrons can interfere with themselves, creating patterns characteristic of waves. This duality isn't limited to light. Matter, too, exhibits wave-like properties. Louis de Broglie proposed that all matter has an associated wavelength, a concept confirmed by subsequent experiments. Segment 3. The uncertainty principle. Werner Heisenberg introduced the uncertainty principle, stating that certain pairs of physical properties, like position and momentum, cannot both be known to arbitrary precision. The more precisely we know one, the less precisely we can know the other. This principle isn't due to measurement flaws, but is intrinsic to the nature of quantum systems. It implies a fundamental limit to what we can know about a particle's state. Segment 4. Quantum superposition and entanglement. Quantum superposition allows particles to exist in multiple states simultaneously until measured. Schrödinger's famous thought experiment involving a cat in a box illustrates this concept, where the cat is both alive and dead until observed. Entanglement is another peculiar phenomenon, where particles become linked such that the state of one instantly influences the state of another, regardless of distance. Einstein referred to this as spooky action at a distance, highlighting its counterintuitive nature. Segment 5. Quantum tunneling and applications. Quantum tunneling allows particles to pass through energy barriers they classically shouldn't overcome. This phenomenon is critical in nuclear fusion within stars and has practical applications in devices like tunnel diodes and the scanning tunneling microscope. Segment 6. Interpretations of quantum mechanics. Various interpretations attempt to explain the strange behaviors observed in quantum mechanics. Copenhagen interpretation posits that quantum systems remain in superposition until measured, collapsing into a definite state upon observation. Many worlds. Interpretation suggests that all possible outcomes of quantum measurements actually occur, each in its own parallel universe. Pilot wave theory proposes that particles have definite trajectories guided by a pilot wave, combining classical and quantum concepts. Each interpretation offers a unique perspective, yet none can be definitively proven, reflecting the enigmatic nature of quantum mechanics. Segment 7. Quantum computing and future prospects. Quantum computing leverages superposition and entanglement to perform computations far beyond the capabilities of classical computers. Qubits, the basic units of quantum information, can represent both 0 and 1 simultaneously, enabling massive parallelism. While still in developmental stages, quantum computers hold promise for revolutionizing fields like cryptography, optimization, and drug discovery. Closing thoughts. As we conclude our gentle voyage through the quantum landscape, reflect on the profound mysteries that lie at the heart of reality. The quantum world challenges our perceptions, inviting us to embrace uncertainty and wonder. May these contemplations accompany you into restful slumber, where dreams intertwine with the fabric of the cosmos. Chapter 1. What is time? Really? Time is everywhere. It ticks on our watches. It passes of our thoughts. We schedule it. We race against it. We try to save it. But what is it? In the simplest sense, time is the progression of events from the past through the present and into the future. It's how we make sense of change, how we measure movement, and how we structure existence. But time isn't a substance. You can't hold it. You can't see it. It's not like space or matter. It's more like a dimension, a way to place events in sequence. For much of human history, time was measured by the movement of the heavens, the rising and setting of the sun, the phases of the moon, the cycles of the stars. Ancient sundials marked its passing by the movement of shadows. Water clocks and hourglasses came later, and then mechanical clocks gave time a steady, ticking rhythm. Yet, beneath the surface, time is anything but simple. Chapter 2. Newton's time versus Einstein's time. Sir Isaac Newton, one of the great minds of science, saw time as absolute, a river flowing steadily and uniformly, the same for everyone, everywhere. Time was a universal backdrop, indifferent to the happenings of the world. But in the early 20th century, Albert Einstein changed everything. Einstein's theories of relativity revealed that time is not fixed, it is flexible. It is woven together with space into what we call space-time. According to Einstein, time can stretch, it can shrink, it can slow down and speed up depending on gravity and velocity. Imagine two clocks, one on Earth, one orbiting far above in a satellite. The one in orbit ticks faster. It experiences less gravity. This is not science fiction. It's measurable, and it's fact. In fact, your GPS wouldn't work correctly without correcting for time dilation caused by the Earth's gravity and the speed of satellites. Chapter 3. The Arrow of Time. Even though Einstein showed that time is relative, we still experience it in one direction. We remember yesterday. We don't remember tomorrow. Why? This one-way journey is called the arrow of time, and it's deeply connected to a concept known as entropy. Entropy is a measure of disorder in a system. The second law of thermodynamics says that entropy tends to increase. In other words, the universe naturally moves from order to disorder. A broken glass doesn't unbreak. Smoke doesn't return to a cigarette. Ice melts, but melted water doesn't refreeze itself without help. This irreversible flow from low entropy to high entropy is what gives time its direction. It may be that time flows only because entropy increases. Without change, without entropy, time might have no meaning at all. Chapter 4. Time and the Brain. But the physical nature of time is only half the story. What about the time we feel? Have you noticed how time speeds up when you're enjoying yourself, or slows down when you're bored or frightened? Our perception of time is elastic. It's influenced by emotion, attention, memory, and age. For a child, a year feels endless. For an adult, it seems to fly. Neuroscientists believe that our experience of time is constructed in the brain. It's not a passive reception, but an active creation. We stitch together experiences and memory, estimating the flow of moments based on changes we perceive. That's why novel events seem longer. When everything is new, your brain stores more data, making time feel fuller. In contrast, routine days blur together and time appears to vanish. Chapter 5. Time Travel, Science or Fantasy. Now, let us drift into a question that captures the imagination. Can we travel through time? In a sense, we already do. We move steadily into the future, second by second. But can we leap forward or go back? Einstein's equations suggest that under extreme conditions, like near a black hole or at near light speeds, time slows down dramatically. This is known as time dilation, and it's real. But traveling backward in time is another matter entirely. Most scientists believe it's impossible, or at least forbidden by the laws of causality. If you could go back in time, you could change the past, and that brings up paradoxes, like the famous grandfather paradox. Still, theories like wormholes or closed time-like curves tempt the imagination. And while there's no evidence we can build such devices, science hasn't completely ruled it out. Chapter 6. The Beginning and End of Time. Let's pull back now and ask, did time have a beginning? The Big Bang wasn't just the birth of matter and space, it was also the birth of time. Before the Big Bang, time as we understand it may not have existed at all. Asking what came before may be meaningless, and how will time end? Some theories suggest the universe will keep expanding forever, growing colder and darker in a distant fate called the heat death, where entropy reaches its maximum and all energy is evenly spread. In that far future, stars will fade, black holes will evaporate, and time, for all practical purposes, will lose its meaning. Chapter 7. Living with Time. And now, in these quiet moments, think of how time shapes your life, not just in clocks and calendars, but in memories, relationships, and hopes. You are a traveler, passing through a stream of moments, each one vanishing into the past as another arrives. The present is all we truly have. It slips through our fingers even as we try to hold it. But in this moment, in this breath, in this stillness, there is peace. Let the ticking of time slow. Let your thoughts fade like twilight. Chapter 1. A Brief History of the Flat Earth Belief. Long before rockets, satellites, and space photography, ancient civilizations gazed up at the sky and imagined the world in many forms. The earliest humans, observing a seemingly flat horizon, naturally assumed the Earth was flat. But even in antiquity, this idea began to shift. Over 2,000 years ago, the Greek philosopher Pythagoras suggested the Earth was round. Later, Aristotle offered evidence. Ships disappearing hull first over the horizon, and the curved shadow Earth casts on the moon during a lunar eclipse. By the 3rd century BCE, Eratosthenes calculated the Earth's circumference using simple geometry and shadows between cities. He was remarkably accurate. So despite modern myths, the spherical Earth has been widely accepted by educated societies for over 2 millennia. Chapter 2. The Modern Flat Earth Movement. So why, in the age of satellites and smartphones, does the flat Earth theory persist? The modern flat Earth movement began in the 19th century, gaining traction with individuals who mistrusted science and authority. In the Internet age, these ideas found fertile ground in forums, videos, and social media echo chambers. Flat Earthers believe the Earth is a flat disk, often surrounded by a giant ice wall, the Antarctic edge, supposedly guarded to prevent people from discovering the truth. Many deny the existence of space, satellites, and even gravity, suggesting instead that the Earth is stationary and enclosed by a dome. But why do people believe this? Sometimes it's a deep mistrust of institutions. Other times, it's a search for control or for a simple, intuitive explanation in a world that feels overwhelmingly complex. Chapter 3. What the Eye Sees and What It Misses. One of the Flat Earth movement's central arguments is based on personal observation. They say the Earth looks flat, they say. So it must be flat. But the truth is, human senses are limited. The Earth is vast, so vast that its curve isn't easily seen on foot or even in an airplane. It's like standing in a massive field of snow and claiming the Earth is white and cold everywhere. Local observation doesn't equal global reality. From mountaintops, distant ships, or high-altitude flights, subtle curvature can be detected. More powerfully, we have satellite imagery showing a spherical Earth from space. These images are not CGI. They're captured daily by multiple space agencies around the world. Chapter 4. Gravity and the Sphere. One of the most compelling arguments against a flat Earth is gravity. Gravity pulls everything toward a central point. On a sphere, this means all objects fall straight down, toward the center of mass. That's why people on opposite sides of the globe don't fall off. It's also why Earth became a sphere during its formation. Gravity naturally shapes large, rotating masses into spheres to evenly distribute gravitational forces. On a flat Earth, gravity would pull toward the center of the disk, making outer regions feel tilted or unstable. This simply doesn't match our experience of walking, standing, or measuring force with precise instruments. Chapter 5. The Sun, Stars, and Time Zones. If Earth were flat, how could we explain the behavior of the Sun? Flat Earthers propose that the Sun circles above the disk like a spotlight, casting light in selective areas. But this doesn't account for the sharp precision of sunsets, sunrises, eclipses, or time zones. Time zones exist because the spherical Earth rotates. As one side faces the Sun, it experiences day, the opposite side, night. On a flat plane, time zones would be chaotic and hard to explain with the Sun just circling above. The same logic applies to stars. In the northern hemisphere, we see different constellations than in the southern hemisphere. On a flat Earth, everyone would see the same night sky, but we don't. Chapter 6. Planes, GPS, and space travel. Long-distance flights offer another clue. Flights from Australia to South America or from Johannesburg to Santiago make no sense on a flat map. They'd require absurd detours. But on a globe, they follow clear great circle routes, the shortest paths over a curved surface. GPS also relies on a network of orbiting satellites that triangulate your location. Flat Earth models often deny satellites exist, yet GPS, satellite TV, and space communications all function consistently across the world. If these satellites weren't real, the technology would fail. And then there is space travel. Dozens of nations have launched satellites. Private companies like SpaceX live stream launches. The International Space Station is visible from Earth with the naked eye. All of this supports the overwhelming consensus. The Earth is a globe. Chapter 7. Why the Truth Matters. At this point, you may wonder, if the evidence is so overwhelming, why does this theory endure? The answer lies in cognitive bias, psychology, and community. Conspiracy theories provide certainty in an uncertain world. They create an us versus them narrative that's emotionally comforting. Once someone commits deeply, it becomes hard to let go. But science doesn't thrive on belief. It grows through observation, testing, questioning, and evidence. It evolves when proven wrong, and unlike conspiracies, science has no single authority. It's a web of independent thinkers, always challenging and building on one another. Believing the Earth is round isn't about trusting NASA. It's about trusting the evidence you can test yourself, whether it's watching a lunar eclipse, tracking a satellite pass, or observing a ship slowly disappear over the horizon. Chapter 8. Returning to Earth. And now, as the gentle current of logic carries us back from the edges of this theory, let your thoughts settle like dust on a well-used globe. The Earth, beautiful and round, spins silently through the cosmos. It tilts and turns, bringing day and night, summer and winter. It floats with elegance in a dance choreographed by gravity, light, and time. There is no need for illusion. The truth is already wondrous enough. Now, let us journey not just across space, but back in time, back to the beginning of all things, back to a moment when there was no earth, no sky, no matter, no light. Tonight, we gently explore one of the most profound ideas in all of science, the Big Bang Theory. This is the story of how the universe began, or at least how we think it might have. Chapter 1. A universe from nothing. It's almost impossible to imagine, but once, before stars, before time itself, there was nothing. No atoms, no space, no energy, no before. Then, in a moment so brief we cannot even properly measure it, the universe came into being. Not an explosion, but an expansion. Not a boom in space, but the creation of space itself. A sudden emergence of energy, rapidly inflating like a balloon in a billionth of a second. This is the Big Bang. Not a bang at all, but the birth of everything. Chapter 2. What the Big Bang really means. The name Big Bang might sound dramatic, like a cosmic firework display, but it's a little misleading. There was no sound, no bright flash, no empty sky being suddenly lit. Instead, it's better to think of the Big Bang as the moment space itself began to stretch. Imagine dots drawn on a balloon. As the balloon inflates, the dots move apart, not because they're moving, but because the surface between them is growing. That's what's happening to galaxies. They aren't flying through space. They're being carried by space as it expands. This expansion is still happening today, everywhere, in every direction, always. Chapter 3. The clues hidden in the cosmos. How do we know this? What clues did the universe leave behind? One of the first came from light, or rather, the stretching of it. In 1929, astronomer Edwin Hubble discovered that distant galaxies are moving away from us, not just in one direction, but in every direction. The farther a galaxy is, the faster it appears to be receding. This redshift, light stretching as space expands, told us that the universe is getting bigger. And if it's expanding now, that means it was smaller in the past, much, much smaller. Trace it all the way back, and you reach a moment of unimaginable density. That first flicker, the Big Bang. Chapter 4. The Afterglow of Creation. But redshift wasn't the only clue. In 1965, two scientists, Arno Penzias and Robert Wilson, were working on a radio antenna. They kept detecting a soft, persistent hiss of static. No matter where they pointed the antenna, it was there. Unknowingly, they had stumbled upon the oldest light in the universe. The cosmic microwave background, a faint glow of radiation from just 380,000 years after the Big Bang. It is the afterglow of creation, spread evenly across the sky, cooled and stretched over 13.8 billion years. It tells us the universe began hot, dense, and uniform before slowly cooling into the stars and galaxies we see today. It is perhaps the most powerful piece of evidence we have, a fossil of the first light. Chapter 5. The timeline of everything. How did it all unfold? Let's take a quiet walk through the timeline of the universe. 0 seconds, the Big Bang. Time and space begin. The universe is a point of pure energy, hotter than any furnace, smaller than any atom. 10 to the negative 35th power seconds. Inflation occurs. The universe expands exponentially, faster than the speed of light, growing from subatomic size to nearly a macroscopic object. 1 second. The universe cools enough for protons and neutrons to form. Matter begins to take shape. 3 minutes. Light elements like hydrogen and helium are created in a process called primordial nucleosynthesis. 380,000 years. The universe becomes cool enough for atoms to form. Photons, particles of light, are finally free to travel. This is the moment we receive the cosmic microwave background from. 1 billion years. The first stars ignite. Galaxies begin to form, gravity pulling gas and dust into luminous spirals and spheres. 9 billion years. Our sun is born. Around it, a disk of gas and rock slowly congeals into planets. Earth forms. 13.8 billion years. Here you are, on a small blue world, spinning around a modest star, floating in the calm arms of the Milky Way. And as you rest, all of this history gently hums beneath you. Chapter 6. What happened before the Big Bang? It's a natural question. If the Big Bang was the beginning, what came before it? And the most honest answer science can offer is, we don't know. According to general relativity, time itself began with the Big Bang. There was no before because time, as we understand it, didn't exist. But some speculative ideas suggest other possibilities. One is the cyclic model, that the universe expands and contracts in infinite cycles, with big bangs and big crunches repeating forever. Another is the idea of a quantum bounce, that before the Big Bang, there was a prior universe that collapsed, then rebounded into ours. And some theories of multiverses suggest our universe is just one bubble among countless others, each with its own laws, its own beginning. We don't have definitive answers, but asking the question is part of our journey. Chapter 7. The role of quantum physics. In the tiniest fractions of a second after the Big Bang, classical physics breaks down. In its place, quantum physics, probabilities and uncertainty, takes over. At this level, space is frothy. Time is grainy. Particles flicker into and out of existence. Reality becomes blurred. It's in this quantum haze that the seeds of galaxies were sown. Tiny fluctuations in energy, invisible at the time, were stretched by inflation, later growing into the structures we see today: galaxies, stars, planets. From chaos came order. From randomness came the cosmos. Chapter 8. Dark Matter and the Hidden Web. As the universe expanded and cooled, gravity began to sculpt it. But there was something strange. Galaxies were rotating too fast. The outer stars should have flown away, but didn't. This pointed to the existence of dark matter, invisible, mysterious mass that surrounds and supports galaxies. We don't know what dark matter is, but we know it's real. We can see its gravitational fingerprint in how galaxies move and how light bends around clusters. It is the scaffolding on which the visible universe hangs, and it all emerged silently, after the Big Bang. Chapter 9. The Slow Birth of Life. Billions of years after the Big Bang, one small planet found itself in a gentle orbit around a stable star. Here, on Earth, chemicals swirled in ancient oceans, struck by lightning, warmed by volcanic heat. Complex molecules formed. Eventually, one of those molecules began to replicate. And so, life began. Every cell in your body carries the echo of the stars. Every breath is part of this 13.8 billion year story. From a singularity to consciousness, from energy to awareness. Chapter 10. The Future of the Universe. And what comes next? The expansion of the universe continues, not slowing down, but speeding up, pushed by a force we call dark energy. If it continues unchecked, galaxies will drift apart, stars will burn out, and matter will decay. This is the heat death, a future of cold, quiet darkness, trillions of years from now. But that, too, is part of the story. The universe is not a static painting, it's a living, breathing, evolving thing. From beginning to end, it tells a story in stars and silence. Chapter 11. Why the Big Bang Matters. The Big Bang isn't just a theory about physics. It's a lens through which we understand ourselves. It tells us we are part of something vast. It tells us everything is connected, that the atoms in your body were forged in ancient stars, and that the universe is not just a place, but a process that began in fire and still burns, quietly, within you. The Dream of Lamarck. In a time before Darwin's finches and natural selection's triumph, there lived a man named Jean-Baptiste Lamarck. A quiet thinker, a botanist with dreams rooted deep in the 18th century, he sat beneath trees, watching their leaves flutter in the wind. It was there, in the stillness of a late summer afternoon, that Lamarck thought of giraffes. He envisioned them stretching their necks, year after year, reaching for the highest leaves, yearning toward the heavens. And as their desire grew, so too did their necks, so thought Lamarck. Not only did they stretch, but their efforts passed into the fibers of their being, etching change into the next generation, as if whispering to their children, "Reach, and you will grow." The idea was elegant in its simplicity. Traits acquired during a creature's life, muscles formed, skills learned, lengths gained, could be gifted to their offspring. It was a tale of effort made real, a poetic union of struggle and progress. But alas, this dream would not last. As the sun set on Lamarck's life, Darwin's storm began to gather beyond the horizon. The world changed. Mendel's peas sprouted quietly, carrying alleles like hidden scrolls of genetic code. Lamarck's theory, noble and calm, like a letter never delivered, faded into the dim corridors of forgotten science. Yet even now, as we drift into stillness, one can imagine those giraffes, still stretching, reaching upward in a dream that never ends. Chapter 2. The Caloric Whisper. Long before the hum of air conditioners and the sting of ice cubes on warm skin, there was a theory. Caloric. A ghostly fluid, weightless and invisible, thought to flow from hotter to colder bodies, like a secret stream in a quiet forest. Scientists believed in its presence as surely as they believed in the pull of gravity. Heat, they claimed, was not energy, but a substance, caloric, that seeped through objects, from flame to kettle, from kettle to air. They built instruments with care, attempting to catch this mysterious essence, to measure the weight of warmth. It was comforting in its way, simple, predictable, like knowing every star in the sky by name. But time is unkind to comfort. experiments grew sharper. Benjamin Thompson, Count Rumford, watched as cannons were bored and metal grew hot, not from the addition of a fluid, but from motion itself, the turning of drills, the grinding of metal, friction. Slowly, the caloric faded like fog in morning light, replaced by energy, thermodynamics, and entropy, the new gods of heat. And yet, in the silence of night, when a blanket holds in the last warmth of day, one might still imagine caloric, curling like steam from a teacup, lingering in the gentle hush. Chapter 3. Phlogiston's Empire. There was a time when fire was magic, and in that magic lived phlogiston. It was the soul of flame, the spirit of combustion. Everything that burned, wood, coal, oil, was believed to contain it. Phlogiston was released in fire, drifting upward in the crackling air, leaving behind ashes like footprints of its departure. Becker and Stahl, thinkers of the 17th century, spoke of phlogiston with reverence. It explained why metals turned to powder in fire, why wood vanished, leaving only the shadow of itself. They said phlogiston was real, though no eye could see it. But science, like time, waits for no theory. Antoine Lavoisier, with balance and breath, weighed air and matter. He saw what others ignored. Fire did not release a substance, it consumed one: oxygen. In one elegant series of experiments, he swept phlogiston into history's attic. Still, the story remains: a flicker in the hearth, the final glow in burnt logs. As you drift further into rest, imagine that ember, slowly dimming, taking with it the last whisper of phlogiston, glowing gently into the void. Chapter 4. The Steady Silence of the Cosmos. When you gaze into the night sky, dotted with stars that twinkle like forgotten dreams, you are staring into a mystery long pondered. In the early 20th century, a belief arose that the universe was eternal and unchanging. It was called the steady-state theory. This model, calm and perpetual, proposed that as the universe expanded, new matter simply appeared, maintaining a constant density. No beginning, no end. Just an infinite unfolding of stars and galaxies, emerging like ripples in an endless pond. Fred Hoyle, Hermann Bondi, and Thomas Gold imagined this serene cosmos, free from cataclysm and singularity. To them, the universe was not born. It simply was. But then came the echo of a bang, a background radiation, soft and omnipresent, like a lullaby of the cosmos. Discovered by Penzias and Wilson, this faint noise spoke of a fiery beginning, a moment of unimaginable heat and light. The Big Bang eclipsed the steady state, and the universe was given a birth. Yet in the quiet of the night, the idea of an eternal, unbothered cosmos still lingers. A sky that never changes. A universe. That simply is a comforting thought for restless minds. Chapter 5. The Clockwork of Laplace. In the corridors of classical physics walked Pierre-Simon Laplace, a mathematician with a mind of precision. To him, the universe was a grand clock, every gear in motion, every outcome determined. He imagined a demon, not evil, but omniscient. Laplace's demon, a being who, knowing the position and velocity of every atom, could predict the entire past and future of the universe. Cosmic certainty. There was no room for chance, no mystery. Everything unfolded from initial conditions, like a book written from its first word to its last. But quantum mechanics stirred. Heisenberg's uncertainty cracked the crystal of certainty. Particles danced unpredictably. Probabilities replaced absolutes. Laplace's demon now sleeps, if it ever lived at all. But in the rhythm of ticking clocks, in the swing of pendulums, in the swirl of galaxies, there's still a whisper of that old dream, that everything can be known if only one could see far enough. Chapter 6. The Last Stretch. As the night deepens and thoughts grow slower, let us return to the giraffes, the caloric, the phlogiston, the steady state, and the all-knowing demon. They are no longer true, but they are still stories. Stories built with care, with curiosity. Science, after all, is not just discovery. It is dreaming with discipline. Let these tales lull you. Let their calm logic and gentle failure soothe your mind. They are not lies. They are stepping stones, missteps on the path to truth. In a world that moves fast, they offer stillness. Ideas once held tight, now released gently, like leaves on a quiet stream. Close your eyes. Breathe deep. The theories are resting. So should you. The origin and initial molecular configuration of deoxyribonucleic acid, also known by its more concise abbreviation, DNA. At this juncture in geologic history, the conditions for life as we now define it did not yet exist. There were no organisms, no cells, and certainly no coffee. There was, however, a rather dynamic combination of inorganic compounds, including but not limited to hydrogen cyanide, methane, ammonia, water vapor, and trace elements of sulfur and phosphorus. These molecules, humble and inert by nature, would one day, through an extraordinarily slow and inefficient process, contribute to the synthesis of the building blocks of life. Let us now consider the concept of abiogenesis, a term derived from the Greek a, meaning not, and bios, meaning life, and genesis, meaning origin. The theory of abiogenesis posits that life arose naturally from non-living matter. It is a concept of great significance and even greater complexity, as it suggests that life did not appear through miraculous intervention, but rather through the gradual chemical evolution of simple molecules into complex macromolecules via pathways such as the Formose reaction, the Strecker synthesis, and possibly, if one accepts the hypothesis, the iron-sulfur world theory. At this point, it is important to note the difference between ribonucleic acid, RNA, and deoxyribonucleic acid, DNA. RNA, which differs from DNA by the presence of a hydroxyl group at the 2' position of the ribose sugar, is believed by many researchers to have preceded DNA in the biochemical chronology of life. This theory is known, perhaps unsurprisingly, as the RNA world hypothesis. According to this model, RNA molecules, due to their dual ability to store genetic information and catalyze chemical reactions, may have played a foundational role in early molecular biology, as it was at the time. However, we are not here today to talk about RNA. That would be a tangent, and tangents, while sometimes interesting, can delay our inevitable approach to the primary topic, DNA. Now, let us examine DNA, or deoxyribonucleic acid, in its basic structural form. DNA is a polymer composed of nucleotide monomers. Each nucleotide consists of 3 distinct subcomponents: a phosphate group, a deoxyribose sugar, and a nitrogenous base. The nitrogenous bases include adenine A, guanine G, cytosine C, and thymine T. It is crucial to remember that adenine pairs with thymine via 2 hydrogen bonds, and guanine pairs with cytosine via 3 hydrogen bonds. This is known as complementary base pairing. This property contributes significantly to the helical structure of DNA. Speaking of helices, it may be of some interest, though perhaps not much, to note that DNA most commonly exists in the B-form double helix. This configuration, characterized by a right-handed twist and approximately 10.5 base pairs per helical turn, was elucidated in 1953 by James Watson and Francis Crick, with notable, though under-recognized, contributions from Rosalind Franklin, whose X-ray diffraction images of DNA were instrumental, though the resolution of said images remains, even now, a topic of reflection. Returning to the subject at hand, let us delve now into the theoretical models of the formation of the first DNA molecule. Although there exists no direct evidence, either paleontological or molecular, of the precise moment or location of this event, various hypotheses suggest a likely environment. One such hypothesis involves the concept of hydrothermal vents, specifically the alkaline hydrothermal vent theory. These underwater fissures, found at mid-ocean ridges, provide gradients in pH and temperature, which are hypothesized to facilitate the polymerization of nucleotides into strands. However, critics of this hypothesis point to the instability of phosphate bonds in such environments. Others suggest that the first DNA may have formed not in hydrothermal vents, but in shallow tidal pools, or perhaps within clay matrices where charged surfaces could have stabilized nucleotide interactions. In any case, once formed, the DNA molecule had to achieve replication, a feat not simple by any standard. Without enzymes, the replication process is inefficient and error-prone. Yet somehow, through trial and error and over countless cycles of polymerization, degradation, a self-replicating DNA strand may have emerged. This would mark the beginning, not of life per se, but of heredity, crucial step toward the origin of living systems. And now, let us pause, not for dramatic effect, but to allow for the contemplation of the staggering slowness of this process. Picture molecules drifting in an aqueous environment for millennia, occasionally bumping into one another, forming transient bonds, most of which promptly degrade. Do we even care? The psychological resistance to metrication. Let us begin. Chapter 1. Introduction to metrication. Metrication, by definition, is the process of converting a system of measurement to the metric system. The metric system, formerly referred to as the International System of Units, SI, is based on powers of 10. This feature makes it, according to numerous studies and experts, both rational and practical. It is composed of units such as the meter, the kilogram, and the liter. 1 kilometer is 1,000 meters. 1 kilogram is 1,000 grams. The logic is consistent. The conversions are simple. The philosophy is elegant in its decimal linearity. Yet despite this clarity and ease of use, resistance to metrication continues, particularly in countries such as the United States of America, Liberia, and Myanmar. Why is this the case? What deep-rooted cognitive forces are in play when citizens express disinterest, confusion, or even hostility toward metric units? This, dear listener, is what we shall now examine. Slowly, painstakingly, in detail, and at length. Chapter 2. A brief, redundant history of measurement systems. Prior to the adoption of the metric system, various measurement systems were used across different civilizations. These include the Roman system, the Chinese shichen and qi, the Egyptian cubit, and the English imperial system. The imperial system, which includes inches, feet, yards, and miles, is not based on powers of 10. For example, 12 inches make a foot, 3 feet make a yard. A mile is 5,280 feet. This inconsistency may not pose a major issue to those accustomed to it. but it introduces considerable cognitive load when performing calculations or conversions. Yet, oddly, many individuals still prefer this system. Why? The answer is not necessarily logical. Chapter 3. The Metric System, an overview that feels longer than it is. The metric system, standardized during the French Revolution, was intended to introduce order, logic, and uniformity to measurements. It was a utopian reform, anchored in Enlightenment values, and it has been adopted by almost every country on Earth. The SI system includes length, meter, m, mass, kilogram, kg, time, second, s, electric current, ampere, a, temperature, Kelvin, K, amount of substance, mole, mole, luminous intensity, candela, CD. Each of these units can be modified with prefixes such as milli, centi, kilo, and mega. These allow for the seamless scaling of measurements. Yet metrication remains incomplete, especially in socio-cultural and psychological terms. Chapter 4. The Psychology of Measurement. Familiarity. Humans are creatures of habit. This is not a novel or provocative insight. Cognitive psychology tells us that familiarity breeds not only comfort, but also fluency. Measurement systems, though technical, are embedded in cultural routines. We cook using cups and ounces, not milliliters and grams. We describe our height in feet and inches, not centimeters. Weather is reported in Fahrenheit, not Celsius. For individuals raised with one system, another feels foreign, even threatening. The term psychological inertia describes this phenomenon. It refers to the resistance people exhibit when asked to change long-standing habits, even when the proposed change is demonstrably superior in efficiency or simplicity. The resistance is not necessarily active, it is often passive. A shrug, a sigh, a comment like, "Why fix what isn't broken?" This, in effect, is the resistance to metrication. Chapter 5. Educational entrenchment. Another significant factor contributing to the resistance to metrication is the early educational system. Children who learn to measure using inches and feet internalize these concepts. Their mental models for distance, volume, and temperature are constructed around the imperial framework. Changing this later in life is difficult. It requires not only unlearning, but remapping mental associations. For example, the tactile sense of what a foot looks like must be replaced with an abstract understanding of 30.48 centimeters. The ease of recall is disrupted. Multiple studies, none of which are particularly engaging, have shown that the more deeply entrenched a measurement system is during early cognitive development, the more challenging it is to override with new information. This leads to what we might call metrication fatigue. Chapter 6. Cultural Identity and the Measurement of Pride. In some regions, notably the United States, imperial measurements are often tied to national identity. The yard and the mile are not merely units of length, they are, metaphorically, units of tradition. Resistance to the metric system is framed by some as resistance to global conformity. This can be analyzed through the lens of social identity theory. Individuals derive part of their identity from group membership. If the group norm includes using pounds and ounces, switching to grams and kilograms may feel like abandoning part of that identity. Surveys indicate that the reluctance to adopt the metric system is often framed not as a rational preference, but as an emotional one. Statements such as, "That's just how we do it here," or "I don't like the metric system," reflect this effective resistance. They are not arguments. They are declarations. Chapter 7. The media's role in metric apathy. Media representations further cement public disinterest in metrication. In American television and film, characters rarely refer to distances in meters or temperatures in Celsius. Instead, we hear about a 6-foot-tall man, or it's 90 degrees outside. This linguistic reinforcement maintains the imperial system's cultural dominance. There is little urgency in the media to shift toward metric language. News outlets, sports broadcasters, and popular science programs continue to present measurements in imperial units. And even when dual measurements are shown, the imperial figure is usually listed first. This leads to exposure bias. The more one is exposed to a format, the more natural it seems, regardless of its logical underpinnings. Now that we have touched upon the foundational aspects of metrication resistance, we shall, in upcoming sections, explore more deeply the roles of governmental policy, cost analysis of metrication efforts, anecdotal failures, and the largely indifferent public response. Chapter 8. Governmental Policies and Bureaucratic Half-Measures. In the realm of legislative history, many governments have attempted metrication with varying degrees of success, failure, and, most commonly, ambivalence. For instance, the United Kingdom began its formal metrication process in 1965. It is now several decades later. Today, Britons buy petrol in litres, but order a pint at the pub. Road signs display miles, while medical prescriptions might use milligrams. The United States took steps toward metrication in 1975 with the Metric Conversion Act, which declared metrication the preferred system of weights and measures for U.S. trade and commerce. However, the same act included a key clause stating that metrication would be entirely voluntary. This, as one might expect, resulted in limited progress. Bureaucratic inertia prevailed. Government agencies adopted piecemeal changes, but the general public was left uninvolved and uninformed. This is what experts refer to as an incomplete transition, a phenomenon wherein a government or institution begins a systemic change but does not complete it, leading to confusion and disinterest. In such cases, the metric system becomes a sort of bureaucratic wallpaper, technically present but largely ignored. Chapter 9. Financial Arguments That No One Cares to Examine. One of the most frequently cited reasons against metrication is cost. Opponents claim that converting road signs, product labels, educational materials, and industrial machinery would be prohibitively expensive. While this is partially true, the figures are not as catastrophic as often portrayed. In Australia, for example, the cost of metrication in the 1970s was approximately 83 million Australian dollars over a 10-year period. That's roughly equivalent to the modern annual budget of a modest urban transit authority. For a nation, it was manageable. Yet in other countries, the perception of financial burden has loomed large. When people hear that it would cost billions, they tend to stop listening, whether or not the figure is accurate. Furthermore, industries that do adopt metrication often report long-term cost reductions due to easier international trade, simplified inventory management, and reduced conversion errors. However, these savings are often long-term and abstract, two qualities that rarely inspire immediate action or emotional engagement. And so, resistance remains. Chapter 10. Anecdotal Misfires and Metric Mishaps. No discussion of metric resistance would be complete without a few cautionary tales, stories used to justify why switching is too risky. One frequently cited example is the Mars Climate Orbiter mission by NASA, which was lost in 1999 due to a failure to convert imperial units to metric. The spacecraft was supposed to use newtons for thrust, but data was provided in pound force. The result? A $327 million spacecraft disintegrated in the Martian atmosphere. To be clear, this error was not a failure of the metric system, but of incomplete metrication. It was the result of dual system confusion, where one engineering team used imperial and the other used metric. In other words, a system halfway changed is often worse than one not changed at all. Yet, such anecdotes stick. They fuel arguments that metrication is error-prone when in fact, dual system operation is the real culprit. Despite that, these narratives become part of cultural lore. They are cited in casual conversation and in online comment sections with a sense of vague certainty and an undertone of, "See, told you so." Chapter 11. The Role of Indifference. Interestingly, most people are not actively opposed to metrication. Rather, they are profoundly indifferent to it. This passive resistance is the most potent of all. Social scientists refer to this phenomenon as apathetic inertia, a lack of action not due to opposition, but due to a lack of motivation. People often report that while they understand the logic behind the metric system, they don't care enough to switch. When something isn't immediately relevant to daily life, it gets filed away in the mental category labeled meh. Public polls in the United States have consistently shown that while less than 30% of people support metrication, even fewer are against it. The majority simply do not think about it at all. This creates a challenge for reformers, as enthusiasm is low, but so is opposition. There is no great battle over measurement, only a long, slow yawn. Chapter 12. Measurement and Emotional Anchoring. Another subtle but powerful force is emotional anchoring. People form emotional attachments to familiar measurements. For example, consider body temperature. In Fahrenheit, a healthy human temperature is 98.6 degrees Fahrenheit. This number feels precise, familiar, and oddly comforting. In Celsius, the equivalent is 37 degrees Celsius, which sounds round. And round, in this case, is perceived as vague, unscientific, possibly lazy. The same happens with height. Being 6 feet tall sounds impressive. Being 183 centimeters tall feels clinical, European, and unsettling. Not bad, just unfamiliar. This emotional anchoring extends to cooking, cups versus grams, driving, miles versus kilometers, and even weather forecasts. Over time, these numbers become emotionally loaded symbols, even if their scientific basis is arbitrary. Chapter 13. Metrication and the Politics of Change. Even change backed by logic and data, is rarely popular when it affects routine. Metrication is no exception. In many places, it has become a political football, seen by some as an imposition by globalist bureaucrats, and by others as a common-sense modernization effort. This polarization is driven less by measurements and more by the framing of the issue. When metrication is framed as taking away tradition, resistance increases. When framed as bringing us in line with science and trade, support rises modestly. However, In the absence of a consistent and sustained messaging campaign, the issue simply drops off the public radar. And when the public forgets, so do the politicians. Chapter 14. Children, Curriculum, and Confusion. Education is another realm where the battle between metric and imperial continues. In the US, science classes use metric. Math classes might use both. Home economics often sticks with imperial. The result is that students grow up with dual fluency, but not necessarily with clarity. This creates a scenario where people may know that there are 2.54 centimeters in an inch, but cannot visualize what a centimeter actually looks like. Or they may remember that 1 kilogram equals 2.2 pounds, but always need a calculator to apply it. This fragmented familiarity does not produce a confident population. It produces metric reluctance, masked as metric ignorance. Chapter 15. Retail, Packaging, and Cognitive Load. Walk into any American grocery store, and you'll see labels showing both metric and imperial units. A carton of milk reads 1 gallon, 3.79 liters. A package of beef might say 16 ounces, 454 grams. The metric is there, technically, but it is never emphasized. This dual labeling adds cognitive load without delivering any benefit. Because the imperial number is listed first and more prominently, shoppers default to it. The metric figure becomes visual noise, always present, rarely noticed. Retail environments are not designed to teach, they are designed to sell, and thus, the educational value of dual labeling is minimal at best. Chapter 16. Resistance as a Social Ritual. In some communities, resisting metrication is part of a broader identity performance. Jokes about Celsius and meters become shorthand for, "we're not like them." It's an inside joke, a ritual, a bonding mechanism. This resistance is not born of ignorance, but of alignment. Measurement systems become yet another axis in the culture wars, like paper straws or daylight saving time. In such environments, the more someone explains the benefits of metrication, the more others resist, because now the issue is no longer about measurement, but about being told what to do. Chapter 17. Global Uniformity, Local Dissonance. The global economy increasingly demands metric usage. Scientific journals, international engineering standards, pharmaceuticals, and most global manufacturing rely on SI units. Yet, local cultures remain non-uniform. This creates measurement friction, a term coined to describe the mental and operational tension caused by simultaneous metric and imperial usage. While large organizations quietly adopt metric internally, the public face remains imperial. This dual existence is sustainable for now, but may not be long-term. However, because the change is slow and undramatic, most people simply do not care. Or if they do care, they do not care enough. Chapter 18. A future where no one notices the change. Experts suggest that the most likely path to full metrication is invisible transition. It is, institutions slowly switch over while not emphasizing the change. Generations grow up with metric tools and references. Eventually, imperial fades not through policy, but through apathy. This has already occurred in industries like science, medicine, and auto manufacturing. Metric is already the default behind the scenes. Over time, more devices, thermometers, fitness trackers, apps display only metric. Children grow up using grams, milliliters, and kilometers without questioning it. In this model, resistance is bypassed not by confrontation, but by patience. Chapter 19. Do we even care? Revisited. So we return to the titular question. Do we even care? And the answer is, overwhelmingly, not really. Metrication is not an issue that inspires protests or parades. It is neither villain nor hero. It is a footnote, a background process, a setting you scroll past when setting up your phone. This lack of engagement may, paradoxically, be what finally allows metrication to succeed. For in silence, change can occur without resistance. Chapter 20. Conclusion. A yawn wrapped in a sigh. In conclusion, the psychological resistance to metrication is not about logic, science, or economics. It is about habit. It is about emotional attachment, institutional drift, cognitive load, and the human tendency to prefer what is familiar, even if it is suboptimal. We have covered history. We have examined inertia. We have strolled through anecdotes, surveys, and societal rituals, and yet the answer remains dull, slow, uncompelling. Metrication will continue, most likely, eventually, quietly, and no one will care, because that, in the end, is the most powerful force in this story. Profound, metric, indifferent boredom. Thank you for your attention. Or rather, thank you for your slow, peaceful descent into sleep.